Hello everyone, welcome to my presentation. My name is Buse. Throughout the summer, I worked with Irish Center for High-End Computing remotely. In this video, I will be presenting my project GPU Acceleration of Breadth-First Search Algorithm in Applications of Social Networks. Before we start, let me give you a brief introduction. Graphs are widely used in representing many practical applications, such as social networks, computer networks, and data organization. They consist of vertices and edges, and breadth-first search, BFS, is one of the core graph-based searching algorithms. In this research, serial and parallel BFS algorithms are implemented on CPU and GPU respectively, and performance analysis are examined. First of all, we need graphs to perform these algorithms, so we generated them by Kronecker generator, which is a routine in Graph 500. Now we need to represent these graphs. So I use dynamic and static data types for representation, which are QData structure and CSR, which stands for compressed sparse row, and it stores graphs compactly with minimum overhead. There are different approaches for BFS algorithm, such as top-down, bottom-up, and hybrid. I implemented a top-down BFS algorithm using a queue. Well, how does this algorithm work? We start with a vertex to traverse, we visit the vertex and mark it as visited and add to the queue. Now we discover the unvisited neighbors of the vertex and we add them to the queue. Then we remove the source vertex from the queue and explore the next vertex in the queue. This algorithm is implemented static and dynamic. In the y-axis, we have edges, and in the x-axis, we have mTabs. Tabs stands for traversed edges per second, and it is a performance metric in Graph 500. As you can see, since CSR graph has lower overhead, it performed better. These results are acquired with relatively small graphs. The largest graph we used is called toy graph in Graph 500 routine, which is scale 26. So, consider a friendship network on Facebook. There are 2.7 billion monthly users on Facebook. Every user is represented by a vertex, and the relation of a user with other users is represented by an edge. So, we have 2.7 billion vertices, and processing such large-scale social network graph is very challenging. Serial implementation of BFS on CPU to analyze this graph is slow. Therefore, we need high computation power, and for that purpose, GPU is utilized. So, to achieve high performance, parallel implementation of BFS on GPU using CUDA is a way to speed up the processing of large graphs. So, how do we parallelize BFS? In each BFS level, we simply traverse all vertices in the queue in parallel by CUDA threads and create a new queue. Now we have parallel and serial BFS code. Let's compare the results. In the table, we see the number of vertices and the edges of graphs, and how the parallel and serial code performed for these graphs. As you can see, the parallel BFS is much faster than the serial implementation. Remember, these results are achieved using K Supercomputer. Its GPU has 16 nodes with Intel Xeon Gold 6148 with the addition of 2 NVIDIA Tesla V100 GPUs on each node. Before we finalizing the video, let's have a look at the profiling tools. NVProf creates detailed profiles of where codes are spending time and what resources they are using. NVVP collects and analyzes the low-level GPU profiler output for the user. It gives timeline analysis of the running code. NVIDIA Insights Compute is an interactive kernel profiler for CUDA applications. We see kernel launch and add a baseline to compare them. It gives detailed workload analysis, different statistics, and occupancy of hardware. Thanks for watching.